Okay, so today and for the rest of November, so that's at least the next 2 weeks following today, so 3 weeks in total, we're going to look at material which, through past experience, I know is quite abstract for half the class. So in particular, students from Ishara and Financial Mathematica, if there are any students from Financial Mathematica, will probably find this material quite abstract. Because of that, I'm going to try not to put too much material into any individual lecture. So actually today's lecture, I don't know if we're going to take the whole 3 hours with it. We'll see how long it takes to present the material. For those of you who are doing Mathematica as your degree subject and are used to abstract material, maybe apologies if I'm going to go through it rather slowly for your taste, but the reason is that half of the class normally have some difficulties with it. And what we're going to be looking at in these 3 weeks is what you might call core computability theory. So we've got the basics set up now. We've got the machine models. We've got lots of machine models after last week, but in particular, the two that we're mainly focusing on. So Turing machines on the one hand, and it's not really a machine model, but nevertheless, it's a model of computation which given by the partial recursive functions, so functions on the natural numbers that have this very nice, clean mathematical definition. And then whichever approach one takes, once one's established the basic definitions of computability, one then starts to look at what kind of problems are computable, what kind of problems aren't computable, and looking further on at sort of more elaborate concepts that are to do with whether or not we can compute things. And for that, one could pick any one of the models. But when one's doing mathematics, it's easier to work with numbers than, say, words over an alphabet, because numbers are just simply simpler. A simpler concept that we're used to dealing with natural numbers ever since primary school, except in those days 0 wasn't a natural number. But apart from that minor issue, we've been used to dealing with natural numbers. And what we're going to do is we're going to look today at concepts from computability as they can be cleanly expressed using just natural numbers. So thinking about just computability in terms of natural numbers. So if we wanted a model of computation, the underlying model of computation is the partial recursive functions, but we can equivalently view that as the Turing machine model because we established the computability of the partial recursive functions via the Turing machine model. But today what we're going to do is we're going to look at the concepts of computability with respect to natural numbers without referring to Turing machine models at all for the main proofs. And we're going to see how one can just establish a clean theory of computability over the natural numbers. And the main topic we're looking at today, the title of the lecture is Computable and Computably Enumerable Set. We're going to be talking about sets of natural numbers and classifying them according to whether they're what we call computable or, more generally, computably enumerable. And this goes back to a division that we saw already in lecture 2 between decidable and semi-decidable languages. Computable is going to be decidable, and computably enumerable is going to be semi-decidable. But we're just going to be talking about sets of numbers, So a language is a set of words. Here we're going to be talking about sets of numbers. We know how to encode numbers as words, and we know how to encode words by what we did a couple of lectures ago. We know how to encode words as numbers. So can we give the simple definitions? So a subset, a set of numbers, A, the subset of the natural numbers is computable. So computable means decidable. And we want to define this in as clean a way as possible, just using the partial computable functions. So we don't want to talk about Turing machines with accept and reject and things like that, but we already saw how to do this in the third lecture, which was on representations. We saw at the end that decidability corresponds to the computability of a characteristic function. Semi-decidability, this was at the end of lecture 3, corresponds to the computability of a partial characteristic function. And in those cases, we were using computability in terms of computability on words, because underlying our representations, we have representations in terms of words. But now we've established computability directly for the natural numbers. We don't need to refer to words at all. So it's computable, there's a definition of computable, if the characteristic function, total characteristic function, so the characteristic of A from, well, just to talk about things simply, we're going to talk about functions on the natural numbers. Everything's going to be on the natural numbers. Is computable as a function on the natural numbers. So, I mean, this is trivial stuff. The characteristic function is just the indicator function, as it's also called, the set A. So this is defined to be, we apply that to a number n, then we get back 1. If n belongs to the set A, then 0. And so we already saw, as I said, something very similar, only using computability via representations in lecture 3 as a characterization of decidable sets. So here, this is our notion of decidability for a set of numbers.
I'm thinking, sorry, is this into the natural is on purpose? So we're just encoding the booleans as 0 and 1.
Yes.
Okay.
Yeah. Well, 1 is true and 0 is false, which I say because Daverin's, because I say that just because Daverin's doing the exercise classes and he normally switches those around. So it obviously doesn't matter. I mean, there are good reasons for his choice. But anyway, this is the usual characteristic or indicator function. And computably enumerable is the analog of semi-decidability. And it's not just the analog of semi-decidability. I mean, a set is computably enumerable if and only if it's semi-decidable according to the definitions in lecture 3 from the representations. That follows from everything we've done. Here we're just establishing simple definitions. So computably enumerable if the... Does anyone remember what comes here? What's the analog in terms of characteristic functions for semi-decidable? The partial characteristic function we use. Very good. Partial characteristic function is computable as a partial function. Partial characteristic function. That's psi. We use a superscript P for partial, subscript N. So now this is a partial function, so when you do the partial arrow, it's computable as a partial function. So just to remind you, partial characteristic function of a number is again 1 if the number belongs to A, But in the case that the number doesn't belong to the set A, it's undefined. Otherwise, so of course I should, because it can be undefined, I should write Kleene quality. Right, jolly good. And then when we defined decidable and semi-decidable in lecture 2, one of the first things we did was, when we defined decidable, was we showed a language that was not decidable, and then we showed that that language was semi-decidable, and that language was the well, the version we used, it was like a version of the halting problem, but the version we used, it was this L accept, so the language of encodings of Turing machines together with their input such that the machine accepts the given encoded input. But it has a slightly complicated definition. And one of the nice things when one's dealing with numbers is that all the definitions become a bit crisper and cleaner, but more abstract. And so our analog of the language that was just not decidable but semi-decidable is a very important subset of the natural numbers, which is Kleene's halting set. Which is universally known in computability theory as K, or I guess K stands for Kleene. I mean, it must do, but don't actually know historically that that's really the case, but it must do. And K, set of numbers. So we had before, as I said, our not decidable, our undecidable, but nonetheless semi-decidable language was the language of encodings of Turing machines together with inputs such that they accept the input. Here we're just going to give single numbers, but we want to somehow, our analog of accepting is going to be that that a certain function is defined. And what we do is we take the numbers E, so E is a natural, so this is natural numbers E. And whenever I use E, it means I'm going to use E as an index for either a computable function or for something else later on. But so it's going to be E such that if we remember from 2 lectures ago, we enumerated the partial computable functions, the computable partial functions. So phi sub E, that's our E indexed computable function. And one can define this in many ways. So one could just say phi of E applied to 0 is defined. So the Turing machine E, if you want to think in terms of Turing machines, the Turing machine E halts when the thought of as a computable function on numbers, partial function on numbers halts when given the input 0. That would give us a definition that's equivalent to the one that we actually use, but a bit more awkward to work with. The nice thing that works is to build a bit of diagonalization into the definition of K itself, and that's so this just tends to give the cleanest proofs of everything. So we take the number E, we take the E Turing machine, and we apply it to itself. We take the E partial recursive function, and we apply it to E, we wait to see if it terminates. And if it terminates, the number E is in our halting set K. And this gives very clean proofs. So let me give you an example of a very clean proof. Well, as I said, it's our analog of the halting of the accept language from lecture 2. So the 2 properties we want to establish are that it's not decidable, that is, not computable, and it's not computably but it is computably enumerable. Mind you, I've just moved the camera, but never mind. Just to say, computable, people sometimes, traditionally this was called recursive, and it's also equivalent to decidable. So these are other names for it. Computably enumerable was traditionally called recursively enumerable. Recursively enumerable, but people tend to prefer computably enumerable nowadays. And that's also equivalent to semi-decidable. Right, so the first very clean proof is a proposition in the notes. It's proposition 7.3 that K is not decidable, that is, it's not computable. So K is not computable. So we had proof of that for the exact language in lecture 2. Here, the proof is like 3 lines long. Well, it depends how long you write the lines, but anyways, it's very short proof. So we want to show it's not computable, so we suppose it is computable. So if it's computable, it means its characteristic function is computable. So its characteristic function, which by definition is a total function, exists somewhere in our enumeration of the computable partial functions. That is, there is an index E that can, so for which phi of E computes that function. So there exists. Okay, but we don't actually need that index E, so never mind. I was getting carried away there, forgetting how to do things. If this function is computable, then the function below is also computable. And so this is a partial function. Partial function, where we're going to define H applied to E is, we're going to say it's undefined, so this is cleanly equal, if the characteristic function of K applied to E equals 1, and will return 0 if the characteristic function of K of E equals 0. So of course, this condition, characteristic function of K equals 1, this is equivalent to, that's equivalent to E belongs to K, and this is equivalent to E does not belong to K. But the reason I've written it like this is because I'm making it clear that this is a computable partial function, because it's just a simple composition of computable partial functions. We take the index E, we've assumed that the characteristic function is computable, so we compute the value of the characteristic function E. Well, because it's a characteristic function, we'll get either 0 or 1. We simply do an if then else. If it's 1, we go into a loop, and if it's 0, we return 0. Okay, so this is computable. And now we do what I was saying before. So since H is a computable partial function, it occurs somewhere in our enumeration of computable partial functions. So we have an index E such that phi of E is H. So an index E for the partial function H. So since H is computable, there exists E such that H, such that the partial function H is the E indexed partial recursive function. Remember, we have this is our enumeration of the partial recursive functions or computable partial functions. And then we simply have that if we apply the function phi of E to E, then that holds, well, by definition, if and only if E belongs to K, and if E belongs to K, that holds if and only if H of E does not hold. So if and only if H of E is undefined. And H is phi of E, so that's if and only if phi of E is undefined. So phi of E is defined if and only if it's undefined. So that's a contradiction. So contradiction. End of the proof. On to, well, 5 lines. 6 if you include the contradiction sign at the bottom. Anyway, so that's the first proposition. Analogous to, as I said, our accepting language is not decidable. For our accepting language, we then proved that the accepting language is, however, semi-decidable. So this is very an analogous situation. Proposition 7.4. The notes is that K is computably enumerable. By the way, computably enumerable is very important part of sets, and it's a bit verbose. Everyone normally calls sets just CE, for computably enumerable. So we're going to prove that, but wait to see the proof, but it's again going to be a very short proof, and actually you're not going to need to devote every long. But you're not going to need to, sorry, you're not going to need to wait very long. Right. So basically, today's lecture is going to be about these two classes of sets, commutable ones and the commutably enumerable sets. And we're going to classify them in various different ways. We're going to see lots of equivalent descriptions of when the set is commutable and when the set is computably enumerable. And the first such characterization is going to give us an easy proof of this result. So we're going to use it to show that K is not computably enumerable. So we want to a useful characterization of computably enumerable sets. So this is proposition 7.5 in the notes. Which is a set A. Always our sets of natural numbers is computably enumerable if and only if it is the domain of some computable partial function. I realised actually the way I'm using domain in this course, sometimes when we've got partial functions, I talk about the domain of a partial function to mean the set on which the partial function is defined. The bit unfortunate that clashes with the idea of the domain is just the, when you write the function f goes from the natural numbers to the natural numbers, and it's a partial function, the domain in another sense is the natural numbers, because the codomain is just the left and right hand side of the arrow. Anyway, here I mean domain, namely the set of elements on which it's defined. Sorry? The co-image. Yeah, that would be cool, yes. Nobody talks about co-image. I mean, people often say something like the domain of definedness or something like that, but that's getting a bit verbose. Co-image would be good. So, yeah, I like that. Okay, so let's prove the proposition. So if the set is CE, then it's the domain of some computable partial function. That's immediate because computably enumerable, any set is the domain of its partial characteristic function, and if it's computably enumerable, the partial characteristic function is computable. So this is the left to right. This is just that A is the domain of partial characteristic function, which is computable by assumption. Okay, so that's the easy direction. The other direction is not much harder. Suppose it's the domain of a computable partial function. We need to show it's the domain of a we need to show that its partial characteristic function is computable. So in the other direction, suppose A is the domain of F, which is a partial function from the natural numbers. The domain of F, where F is a partial computable function from the natural numbers, so that partial function is computable. But then we simply define, we simply note that we can compute partial characteristic function of F so the partial characteristic function of A, the partial characteristic function of A by we want an algorithm for computing, or we want a way of seeing the partial characteristic function is computable. We apply that to a number n. This we can compute that by simply running f on n. So we run f on n. If it's defined, we return what? 1, because we want this to be the partial characteristic function. And if otherwise, we're undefined. So this is a Kleene equality. Okay, so why is this computable? It's no longer an if then else. Because we run f on n, but if f on n doesn't terminate, if it's undefined, that means it doesn't terminate. Well, we never get to see it, we never get to know that it doesn't terminate. We can't wait infinitely long, unless we're in the world of hypercomputation, as it was called last week. But we're not. So we can't wait to see, but it doesn't matter because if f of n fails to terminate, well, anyway, we don't need to return anything, we want to not terminate, so that's fine, it's just absorbed into our computation. But if it does terminate, we get that after finite time, and then we say, okay, we've terminated, we'll give back 1. And mathematically, this is just a simple composition of computable partial functions. We have the composition operation on partial functions, and there's the composition of the constantly one function with the partial function f, which is computable. Okay. So that's done. And now we can prove proposition 7.4. So then, sorry, this was I said proof. This is I said proof. This is proof of proposition 7.5. I'm a little bit mixing up the order of things, but now we're going to prove proposition 7.4. And so we want to show K is computably enumerable. So K is this set here, those elements E such that they're such that if we apply the E indexed partial computable function to E, we defined. But K is therefore, K is the domain of the computable function, computable partial function, N, sorry, E, let's say, because E maps to what we want. So it's simply the domain of those, we map E to phi E of E. Okay? But why is that computable? Why is mapping to phi? So for any E, we need to computably extract the results of running the E indexed partial function, computable partial function on E. Why can we do that? Does anyone know?
Yeah.
Sorry?
Now, first find the guy and then
Maybe, I'm not quite sure exactly. So the words I wanted to hear was you use the universal computable function. Okay? This is, remember we had the 2 lectures ago, we had the universal computable function psi, which which takes, in this case, 2 arguments, given an E and an N, it computes phi E, the E index partial computable function applied to N. In this case, we simply copy the E as an argument. Did I call it psi U? Right. So psi U is the universal function. Okay. So there's the domain of the computable partial function, therefore it's completely enumerable. And just to jog your memories, in the second lecture, when we defined the accept language, we directly proved that the accept language was not decidable by a sort of diagonalization, which was in the proof that I rubbed off here. The diagonalization is kind of in the definition of the set K itself here. And in order to prove that the accept language was semi-decidable, which is the analog of computably enumerable, we needed to introduce the universal Turing machine and use that. So here, in the same way that we needed the universal Turing machine in the context of lecture 2, we need the universal computable partial function for proving this result that K is computably enumerable. Okay. Right, so proposition 7.5 is useful to prove proposition 7.4. It's a very easy proposition, but it's also useful for another purpose that's extremely important, and that's the following. So let's go maybe to the left-hand field. So what proposition 7.5 gives us it gives us an enumeration of the computably enumerable sets. So we have the enumeration of the computable partial functions. Phi 0 is the first one, phi 1 is the second one, phi 2 is the third one, and so on, ad infinitum. And you'll see, I think, in today's exercise class, that something that I told you 2 weeks ago, which is that every computable function appears infinitely often in that list, necessarily so. But nonetheless, every partial computable function appears infinitely often in that list. But we can also use that to define now an enumeration of the computably enumerable sets. So we define W sub E. This is the standard notation for the E-indexed computably enumerable set in the enumeration. Simply the domain of phi sub E. So here, if we go through, here we enumerate through every computable partial function, since the since by proposition 7.5, the computably enumerable sets are exactly the domains of partial computable functions. This is enumerating all the computably enumerable sets. So we're going to have a second enumeration later of the computably enumerable sets, which is going to be with a capital E. And one needs to kind of remember which one's which. So the mnemonic I use is W of E is, well, we have domain, and this W is the N in domain inverted. I don't know if it helps you, but, well, and you don't know yet because you haven't done enough computability theory, but when you start in the exercise classes working with these two enumerations, W sub E and E sub E, this is the way to remember that W sub E is the domain. Okay, or anyway, or if you find a better mnemonic, then you can let me know, because I know this one's not particularly useful. Okay, so we've got a representation of the set of all computably enumerable sets. So by the clock on the back wall, it's 5 to 3, but this is actually a very good point for a break. So we're going to break now, and we'll start again at 10 past 3. But by the clock on the back wall, which is not accurate, but that's our reference clock. Well, it might be. It differs from my one. Okay. Right. So we've seen we have an enumeration of computably enumerable sets, and we're now going to get various characterizations of computable and computably enumerable sets. So the first one is, I mean, maybe I'll state it, but then explain why it's interesting. So this is, let's keep the enumeration from the enumeration of results from the lecture notes. So let's suppose we have a set. Let's suppose we have a set that we can define in the following way, where so A is such that there exists a total computable function in two arguments such that for all natural numbers n, or x, let's say x belongs to A, if and only if there exists some z such that, sorry, this is t, let's keep the same notations in the notes, such that t of x z equals 0. No, so I've left some space here because I'm going to complete the writing here. But the point is, we've got some set that's defined in the following way. We've got a total computable function, which we can compute on any pairs. And if we want to test if an x belongs to A, we can do that by searching through natural numbers z to find one such that t of x of z equals 0. So starting with z equals 0, then going up z equals 1, z equals 2, and so on. And it's obvious, fairly obvious, that that gives us a computably enumerable set, because we have a semi-decision procedure for if x belongs to A, namely, look through all the numbers z until we find one such that t of x of z equals 0, and while we don't find one, we continue searching. And it's a semi-decision procedure because maybe we never know that we need to stop the search. If we don't find one, it could just be we haven't got high enough in the set. So it's kind of straightforward that a subset A of natural numbers is computably enumerable if there exists. So that the argument is this. Okay. But in fact, this is the only way of producing this method produces all computably enumerable sets. But this is not just an if, it's an if and only if. And that other direction is more interesting because that other direction is saying every computably enumerable set can be reduced to a search problem for a computable property, that is a decidable property. Okay, so that's the only way of getting computably enumerable sets. Right, so there are two implications. So the right, so proof. So the right to left one is the one I've already argued for. We can prove that formally in the following way. So that's, if we've got such a computable T, we can do this search. Well, we've got a method of doing a search, which is the minimization operation from the lecture on computable, the partial recursive functions. So if we're given a computable T, then if we look at the partial function, this is a total function, but the partial function mu t, so this is total function on the natural numbers, the partial function mu t, which is a unary function on the natural numbers, but it's a partial function. Remember, mu t says, given an x, look for the smallest z such that tx of z equals 0. That's what the minimization does, looks for this. But it says actually return the smallest value such that t of x of z equals 0. And you know, if that search never holds, it's just undefined. But that is clearly computable because it's the minimization of a computable function. And we notice that this partial function has A as its domain. Because if there exists some z such that t of x of z equals 0, then eventually our search will find it because the t is always defined. So that problematic case in the definition of minimization, that all lower values have to be defined. If you remember that from lecture, whatever it was, 4 or something, that problematic case always holds. There's no issue there because everything's defined for t. So this has A as its domain, hence A is computable, hence A is CE by the proposition we had earlier, which is what was it? That we got the domain of a unary computable function is computably enumerable, so by proposition 7.5. Okay. Well, that's the easy direction. The interesting direction is suppose A is computably enumerable. How are we going to turn that? So all this is saying is that the partial characteristic function is computable. How are we going to find a total function that gives us a search problem that we can get t from? So there's an intuitive way of doing this. So A is the domain. So A is computably enumerable. So A is the domain of a computable partial function. And we want to have it as a search problem. So a sort of intuitive thing we can do is that for every number z, we can use z to count the number of steps in the execution of the partial characteristic function of A on X, and kind of run the underlying Turing machine for that number of steps and see if it's computed the value for the partial characteristic function, if it's actually computed the one that partially computable function. And if it has, we return the value 0, otherwise we return some other value that's different from 0. And that's computable because we're running a Turing machine for a bounded number of steps and see if it's terminated with a certain result. And we can use that, so we have to code up a very complicated computable function there, but we can use that as our t. So that's the intuition. We've actually got a technical result that allows us to formalize this easily without talking about steps of Turing machines, because actually the execution of whole configuration sequences of Turing machines was built into the proof of the technical result. And this technical result is Kleene's normal form theorem from 2 lectures ago. So I'm not going to write down the normal form theorem again because it was quite complicated. Let me just write the proof and I'll explain the bits as we go along. So for this implication, suppose A is CE, it's computably enumerable. So then A is the domain of some partial computable function, or in other words, A arises in the enumeration. So then A is in our enumeration of computably enumerable sets for some E. And then, by Kleene's normal form theorem, lecture 5, E belongs to, a number X belongs to A, which means it belongs to the domain of the ETH computable function. Well, if and only if, well, something is in the domain of the ETH computable function, of the E index computable function, if and only if, when we run the Turing machine for phi of E on X, the argument we're giving, phi of E applied to X, because phi of E is a function whose partial function whose domain is A. This terminates, and what this terminates means is that there exists some configuration sequence Z of the whole Turing machine execution such that the T predicate that we have from Kleene's normal form is true, by the definition of the T predicate in Kleene's normal form theorem. So that's, you have to remember from 2 weeks ago, but so this holds if and only if so Kleene's normal form theorem said that for the correct set that represents the whole terminating configuration sequence of the Turing machine representing phi of V, so for that Kleene's T predicate returned 0, or T function returned 0 if and only if this Z was the encoding of the whole execution sequence. So if there exists such a Z, for which this is 0, it means there exists a completed execution sequence such that x is in the domain of E, namely x belongs to W of E, which is A. So this holds if and only if there exists a Z. Now this is a computable predicate, and so we can simply define T of x, Z. So this is a computable function, this T function. So little t of x and Z is simply T applied to E, the index of our computing union is Z. Okay. So that's something, you know, I bet pretty much no one in this room is really comfortable with Kleene's normal form theorem because it was something we did 2 weeks ago. We haven't covered it in the exercise class, but this is a good excuse to think back over it. So read through these notes afterwards and try and understand where this argument comes from. The beauty of this, the beauty of this lemma that we've just proved is that we've now kind of relegated Kleene's normal form theorem to the proof. We don't need to use it anymore because we've now got this very nice characterization of computably enumerable sets in terms of search problems that will often serve a purpose that we can just use it like this rather than having to worry about exactly what this function within T looks like, which is potentially something rather complicated. Okay. Right, so that's a characterization of computably enumerable sets in terms of computable sets. In terms of search problems. That's a nice thing. Sort of going in a different direction, let's look at computable sets. And, whoops. I wonder if this remote control, maybe the battery is getting low. You think if it's got a low battery, does it work? But then I can't see whether it's working with the board. I'm hitting the remote.
Yeah.
All right, let's do it on camera. Oh well, we can see 1.5 boards. I think I'll just use that 1.5 boards for the laptop. Technology. Right, so the next result is to motivate this, suppose A is computed. So if A is computably enumerable, so let's see what this is. Oh, this is a theorem. Bit random what's a lemma and what's a theorem, but anyway. So this is theorem 7.7. So if A is computably enumerable, so A is a subset of natural numbers. Now I'm going to say if, and I want to put the words in later. So if A is computably enumerable, oh, sorry. Yeah, so let's do it like this. So if A is computably if A is computable, sorry, then so I'm going to raise it. I want to raise the question, I'm just trying to work out what's right on the board. Okay. Good. So the question is, sorry about that. So if A is computable, does it follow that A is computably enumerable?
Yes, so if something is decidable, is it also semi-decidable? Yes, of course, because if the characteristic function is computable, you can easily compute the partial characteristic function. What about the complement of A? So here we've got A is the subset of the natural numbers, and the complement of A is just those natural numbers locked in A. Suppose one writes that as A superscript C, but I'm going to write it as A bar. So if A is computable, is the complement of A computable here? Yes, because if A is computable, you can, the characteristic function is computable, you can just subtract the characteristic, you can just do 1 minus the characteristic function, that's obviously computable too, and that's the characteristic function of the complement set. So A is computable implies that A is computably enumerable and the complement of A is computably enumerable. That's quite easy. But guess what also holds? The converse also holds. So a set is computable if and only if it and its complement are both computably enumerable. Okay. So we've already talked through the left to right implication. Let's do the proof of the right to left implication. Now, in a sense, if I were going, to make the lecture really both careful and so it's building nicely on previous development, what I should do for that sort of correct technical development would be to give the proof that uses the lemma here. And the proof that uses the lemma here is a slightly technical proof. It's not too hard, but it's in the notes. So I'm going to let you read the proof in the notes, and that's something you should work through, and it will be helpful, that sort of material, for the exercise class next week. But instead of that, I'm going to give you the hand-wavy proof of this implication, so you understand why it's true, using the Church-Turing thesis. So remember, I said a harmless use last week of the Church-Turing thesis is we can give an informal algorithm and say, well, it's okay because we know that our models correspond to what's informally computable. Then if we give an informal algorithm, then we can turn that into a correct algorithm using Turing machines, or in this case, using computable partial functions. So the informal algorithm is this. So suppose informal using, so this isn't in the notes, but it's more intuitive. Informal using the Church, I'll just write the C2 thesis, the Church-Turing thesis. So suppose A and the complements of A are computably enumerable. So then the partial characteristic functions for each of them are computable. So what we do is we want to define a computational procedure, an algorithm for computing the characteristic function of A. So then we compute characteristic function, or a partial characteristic function, as follows. So on input n, what we do is we run the partial characteristic, we can compute the partial characteristic function for A, and we can compute the partial characteristic for A complement. We run these two partial characteristic functions, we execute them on our machine model in parallel. So we execute the apply the partial characteristic function for A of n and the partial characteristic function of complement of A in parallel. And if you say, hey, we didn't have parallelism in our Turing machine model, well, it doesn't matter. What you can do when you have something parallel, you can what's called interleave the computations. So you've got two parallel threads, you do one step of one, then one step of the other, and then one step of the first one, and one step of the second one, and you keep on going backwards and forwards. And what you do is you wait for one of these to terminate with one. And because n belongs to exactly one of A and A complement, only one of them will terminate. But because every n belongs to one of these two sets, one of them will, exactly, it will always be the case that exactly one of these terminates. So if psi A of n terminates, we return 1 because we belong to A, and if psi is a complement of A of n terminates, we return 0. And we avoid this problem that we don't know how long to wait when we're executing a computable partial function. We don't know how long, we don't know how long to wait for termination because we know that eventually one of these two will terminate. So we have to be patient. We don't know how long to wait, but we know that if we wait long enough, eventually we'll get an answer. And so therefore this is a procedure that terminates, and this computes the characteristic function.
So this is a non-constructive schedule.
This is a sketch of a proof which is constructive if you assume what's called Markov's principle constructively. Okay.
So I'm guessing that the words.
No, wait a minute. No, probably. No, it's probably more than non-constructive. So, interesting question.
Yeah, I'm guessing what the T doesn't. Words constructive.
I'm not sure. Good question. I thought about this before, whether it's constructive or not, and I don't remember. So, but certainly this proof is not. Yeah, so it's a good point. We can think about that in the next break. Right. Anyway, a corollary of, let's put it down at the bottom of the board here. The corollary of the theorem is very important. So, our Kleene halting set K, we showed that it is computable. We showed that it is computably enumerable, but not computable. Therefore, the complement of K is not computably enumerable. Okay? So the corollary, the complement of the halting set K is not computably enumerable. And this is a very important fact. So we're often going to use the halting set and the basic properties being that it is computably enumerable, but its complement is not computably enumerable. Right. Okay, so we had a lemma characterizing computably enumerable sets. We have a theorem characterizing computable sets. We're now going to go back to computably enumerable, and then we're going to go back to computable. So we're going to have one more characterization of computably enumerable sets and one more characterization of computable sets. Yeah, I can't move the camera, so we'll try. So by the way, I mean, this terminology computably enumerable sounds a bit weird, except you might have heard of it before. And as I said, it's also called recursively enumerable. Does anyone know why computably enumerable, maybe you happen to know this as sort of some background knowledge or something, does anyone know why computably enumerable sets are called computably enumerable sets? So, what we've seen in the definition is they're sets that are kind of semi-decidable. We can compute the partial characteristic function, which gives us a positive answer if something's in the set, but doesn't give us any answer if something's not in the set. So,
Is it because we can enumerate them by some computable function?
yeah. So in fact, it turns out that these sets are exactly the sets that we can enumerate with computable functions. So this is where the terminology comes from. But for us, we're not using it as the definition, we're using it as a theorem. And that's the next result. This is the characterization of computably enumerable sets. So this is again a theorem according to the notes. So the theorem following are equivalent. So T, F, A, E, the following are equivalent for a set, a subset of the natural numbers. And we want to be characterizing computable enumerability. So the first one is A is CD. And the third one, so I'll keep the numbering the same as in the lectures. The third one is that A is the range or image is the same thing. Let's keep the notation in the notes. Is Pavia Nojica? Is that right? Is that right? Yeah. Yeah, super. Good. This is in tomorrow's long weekend modules on that one, so I need to learn it. So A is the range, the logogrenosti of a unary, well, the computable partial function, there is one argument, computable partial function. So we're looking at images here of partial functions rather than total functions, but nonetheless the image is just the same. So those values that are taken by applying the partial function to some element of the domain. And almost A is the range or image of a total computable function. But it's not quite. So what else needs, there's another possibility here. So which set is not the image of, is computably enumerable, but is not the image of a total computable function of the natural language? The empty set. So that is, of course, computably enumerable because its partial characteristic function is just the everywhere undefined function, which is obviously computable. So here we need two possibilities. Either A is empty or A is the range of the total computable function. Okay. And both 2 and 3 could be seen as reasonable justifications for the terminology computably enumerable. Yeah. It's we're enumerating the set A in a computable way as the image of, I mean, especially this one as being the range of the total computable function. Right, so so we're going to prove this in a cycle. So let's kill 2 implies 3 first, because it's trivial. So if A is the range of a computable function, of a total computable, function, then of course it's the range of a computable partial function because every total function is computable. If A is the empty set, of course it's the range of a computable partial function because it's the range of the everywhere undefined function. So 2 implies 3 is trivial. Or easy, let's say. Um, right, so the notes again so we need to prove 1 implies 2 and 3 implies 1, because we're going to go around in a cycle. The notes again do these in a kind of formally satisfactory way that doesn't necessarily have all the best intuitions clear in it. 1 implies 3, sorry. So 1 implies, we're going to do 1 implies 2 and 3 implies 1. 1 implies 2 uses that lemma we had earlier. 3 implies 1, again uses the Kleene normal form theorem from the version in the notes. So what I'm going to do here, since we've seen one application of Kleene normal form theorem, so what I'm going to try and do in the lecture is I'll do 1 implies 2, as in the notes, in the kind of, so you get some examples of the kind of formally satisfactory way of doing proofs. So I'll do that for 1 implies 2, and 3 implies 1 I'll do in an intuitive way, okay? Which you can then look in the notes for the formal version of it. But we'll start with 1 implies 2. So the 1 implies 2. So let's get to a nice one. So suppose A is CE, and the empty set case is A is CE. The empty set case is kind of the uninteresting one, but so we need to show this or this, but let's just assume that the left-hand side doesn't apply, and A is not equal, is not the empty set. So A is not empty. So we need to find a total computable function that we get A as the image. So because A is non-empty, we can select some element of A. So select any element which we'll call A sub 0 on the set A. And because A is computably enumerable, by our lemma we had that every computably enumerable set is a search function for a total to find a 0 of a total function in 2 arguments. So by lemma 7.6, as it was, there exists a computable total function. I won't write total, but I'll just use the total arrow. A computable, it was called T in the lemma, but I'm going to call it S here. So S from, at least I think it was called T in the lemma. Anyway, we've got a total function satisfying. So remember, the point of this total function was that membership of A could be reduced to search problem for there exists a Z such that S, Y, Z equals 0. Okay? So this is membership of A by Y. So now, what we can do is we can use our pairing function that was a bijection from previous lectures from natural numbers squared to the natural numbers. So encoding a pair of numbers as a single number. So using the pairing function P from pairs of numbers to numbers, which was the bijection, we have that A is the range, the image of the izračunljivosti of the total computable so we're going to map a number x to, we're going to interpret x as a pair. So suppose to interpret x as a pair and we project out the elements y and z. So suppose x is the p the pair of y and z, and every number is the pair of two unique numbers y and z because it was a bijection. So we return y if s y z equals 0, where x is this pair, and the point of having the little value a0 is so we can make things total and a0 otherwise. And the point is, every y in the set A is going to be in the image of this function, because for every y there exists some z, such that s, y, and z equals 0. And for that pair y, z, we look at the value x equals p of y equals p of y of z, and this function maps that to y. And any other value, it maps to a0, and that's also in the set A. So every element in A is in the image of this function, and every element in the image of this function is in the set A. Okay, so it's only that. Okay, so that's kind of the not too difficult proof of one implies two. So for 3 implies 1, we can either do the formal proof using Kleene's normal form theorem in the notes, or let's see, it's 10 to 4. So I didn't prepare the informal proof beforehand, because I had another lecture before this one. So let me see if I can think of it. And if not, we'll have an early break. And then we'll do this afterwards. But and maybe one of you can think of it. So A is the range of a computable partial function. And we need to show that it's computably enumerable, meaning there exists a computable partial function. It's enough to show there exists a computable partial function whose domain is A. Okay, this looks fairly easy. So we're going to use a kind of, by intuitive proof, I mean a Church-Turing thesis style of proof. So suppose A is the range of F, which is computable. Yeah, this is sorry, no, the range is not computable, where F is computable. F, partial function F is computable. Okay, and we want to find a computable partial function that has that range of F as its domain. So compute a partial function G as follows. Using an informally described algorithm. So G of n is G been equal to run f in parallel on all natural numbers. So now we're not just doing two things in parallel, we're doing infinitely many things in parallel, and wait for one of them to terminate. And if, wait for them to terminate in turn. Some of them won't terminate, some of them will. Each time one terminates, check to see if n is the result of that. So run f on, so run f0, f1, f2, dot, dot, dot in parallel. Parallel until, if it happens, we get f of n terminates with the value n for some n. In which case, return 1. Okay. So if we can run on all infinitely many natural numbers in parallel, just, we're running lots and lots of computations and checking them as they return values. Some of them won't, some of them just keep going forever, but we're running them in parallel. So, we don't, something going on forever doesn't stop us looking at proceeding with other parallel computations. And as and when they terminate, we check the values, and if finally we get one whose value is n, we say, aha, we found our value. And so in that case, we stop, we say, yep, we've got n in the image, and we'll return 1. And if we never get such a thing, never mind, we carry on forever. So we can compute this G, we can do this infinite computation in parallel, and G is the partial characteristic function for A.
For some n, right?
Then, no, we're computing G on, for some n. Yeah, sorry, that's what you said. Yeah, thank you. Yeah. Then G is computable. Well, I said we compute it, then G is the partial characteristic function for set A, which shows is computable, so that shows the imposed figure. How do we run infinitely many things in parallel? Well, again, we do interleaving. But now we have to do the interleaving, we do one step of this one, then one step of this one, then we go back and do one step of this one, then we do another step of this one, and then one step of this one, and then we go back. Yeah, it's like a sort of going through, it's like the bijection between the natural numbers and the natural numbers. Eventually, as you go on, you eventually start on more processes, and as you keep on going back to them, you can keep on doing more steps. Anyway, you can work it out yourselves, and if you're unhappy with this informal but intuitive style of argument, you can have a look at the formally very satisfactory argument in the notes that one gets from using this normal form. Right, now it's 3 minutes to 3 by the clock on the back wall, so we're going to start at 12 minutes past 3 according to our timepiece. Because this is a good stopping point. Any questions?
Again, is there an issue with saying earlier select A0 from A? Can you computably always select?
No, we don't need to computably select them.
Okay.
Right, because and in fact, we're just starting off with an arbitrary subset that's non-empty. So, and if you want to be constructive, you would have an inhabited instead of non-empty. So, yeah, but we don't need to do it confusingly. Right, so we have a characterization of computably enumerable sets as sets that are computably enumerable. So that's the where computably enumerable means one of these two statements here. It's the image of a total computable function or a partial computable function. But this in the notes is theorem 7.9, I think. And the last theorem today is a similar characterization for computable sets. So obviously it can't be the same characterization for computable sets, but it's along similar lines. So I hope we can all see the bottom of the board here, because it just seems useful to have it in the same place to compare. So the theorem 7.10.
That theorem, so it's I we found some like the previous one, so but it was is the corollary number the lowest one.
So yeah, I mean it's actually
It's
it's
not a big deal.
No, thank you, because you see, I said I hadn't put the note, I hadn't actually compiled the note, so what I've got in my hand is a previous year's version of this material, so the numbering is not actually, I didn't realise the numbering was a bit different, but so sorry.
No, but that's all you had it, it's in the new notes.
You just didn't number the corollary.
Yeah.
If you number the corollary, you get that is 7.9.
Yeah, I see, right. No, I'm trying to be consistent with the notes, yeah, with the online notes, not with my own numbering in the lecture. 7.10 is again the following of equivalent for set numbers. And this time we want a characterization of computability, so decidability. So in the notes there are two statements. Well, actually, I'm going to add a third statement, but I'm not going to prove the equivalence with the third statement. And the third statement I'm going to put in the middle because it's a kind of natural one in the middle here. So the one in the middle is similar to the one in the middle here. That either, but let's just call this bullet point. It's not getting a number because we're not going to prove it. So either A is empty, or A is the range of a total computable function that's not just total, but it's also increasing. So A is the range of an increasing total computable function. Where, of course, increasing means, I mean, we all know this, but increasing is if n is less than or equal to n, then f of n is less than or equal to f of n. So it was also monotonically increasing, as the pattern is called. Okay. And the one that is in the notes, and which I'm going to prove, is that we actually going to strengthen this to a strictly increasing total computable function. So or A is the range of a strictly increasing hot well, enough space there. Okay, so once again, if the range of a strictly increasing total computable function, that's not going to include all computable sets. So in this case, what are the sets that we omit? So if you've got a range of a strictly increasing, of course, is you just replace these with strict inequalities. Strictly increasing and strictly less than n implies f of and strictly less than n. So if you've got a strictly increasing function, what property holds of its range or image? It's infinite, yeah. So to be, for A to be the range of a strictly increasing computable total function, it's infinite. So here we want a finite computable set. So A is a finite computable set, or A is the range of a strictly increasing total function. Which finite sets are computable? All of them. Why? Because you can write a program for the characteristic function just in terms of if-then-else statements. You just need a finite number, you got a finite set, you just need a finite number of if-then-else statements to determine if a number is in the set. So here we have A is finite. Okay. So it's an interesting exercise to think about the middle bullet point here with where we're just using weakly increasing rather than strictly increasing, and I'll leave that for you to think about. Okay, it's very non-constructive. Even everything is non-constructive, but this is super non-constructive. This equivalence to this with this second bullet point. So we're going to do the equivalence between 1 and 2. So this is proof. So 1 implies 2. So suppose A is computable, and we need to exhibit A as the suppose A is computable. Then we want to exhibit A as the range of an increasing, well, and A is infinite. Because, yeah, very little. I mean, if it's finite, that's fine, but the interesting case is infinite. We want to exhibit it as the image of a total computable function, and it's kind of very obvious what to do here. So when A is the image of n, maps onto. Anyone see what to do here? I mean, there are various ways of describing it, because
the nth largest element.
sorry?
The nth largest element of A.
Yeah, so we need to find the nth largest element of A, and how do we find it? Well, we simply check through the numbers from 0, 1, 2, 3, 4, and so on, and we can just apply the computable characteristic function to check if each number is in the image. So we just search through n equals 0, 1, 2, 3, 4, 5 using characteristic function of A, which is computable by assumption, to find the, as you say, the nth smallest element of A. Okay. It's a simple algorithm. Let me just test psi A of 0, psi A of 1. When we get one that's in the set, we decrease our counter for n, and we keep on going until we get the nth one in the set. Okay, so that's the easy direction. So 2 implies 1. well, any finite set is computable. We've just talked about that, so we'll ignore that case. So suppose A is the range of a strictly increasing computable critical function. So suppose A equals the range of F, where F is a total function with the natural numbers strictly increasing. Now we need to define we need to show that we can compute the characteristic function of A. Where we compute the characteristic function of A as follows. This board. Follows. And yes, this is also fairly obvious. Sorry. No, yeah, this is right. We want to compute a characteristic function of. So, A for them is simply 1. If the way I process in the notes, if n equals f of x, where x is the smallest number such that f of x is greater than equal to n, and 0 otherwise. So once again, we just do search through, in this case, through f of 0, f of 1, f of 2, f of so on, until we either we're going up the image of f in order, so the f of 0, f of 1, f of 2, f of 3, they're increasing. So eventually we will either get beyond n, and if we skip 10, then we know that n is not in the image, or we'll actually hit n and done with the term 0. Actually, this is a very easy experiment. It becomes quite a bit less easy if you include the middle bullet point here. But this is the in my view, this is the interesting result, the equivalence between 1 and 2. And we're immediately going to get a corollary of it, which is a nice fact, which is going to be useful on a couple of occasions in the future. And it's a non-trivial fact. Versus corollary. Every infinite computably enumerable set has an infinite computable subset. So computably enumerable set is just a set of acceptance intuitively semi-decidable. But we can actually, within that set, find a computable subset. That's an infinite decidable subset. So that's not a totally trivial fact. If you want to, after the lecture, take some time to think about the halting set case that we had at the beginning, that's computably enumerable. It's far from obvious that there exists an infinite computable subset of the halting set. It's not very difficult, but we're going to see it. It's not totally straightforward. So, of course, what we're going to do So to show there's an infinite computable subset, we're going to define a strictly increasing computable function whose image is a subset of the original computably enumerable set. So the proof is let A be computably enumerable. And because it's computably enumerable and infinite, so by the first characterization theorem of computably enumerable sets, A is the image of a total computable function. And in the lecture notes, this is F. So by what's it called? Theorem 7.9, the one with the controversial number. By theorem 7.9, A is the image of F. So I call it image or range. Range. Use the same terminology. Range of F, or some computable F, some computable total function F. Okay, and now we're going to define the computable G that's strictly increasing that falls inside this image. So we simply define by recursion G of n is going to be so by recursion we're going to have a base case. So G of 0 we're simply going to define to be f of 0. So we pick some number in the image, but by this only the one that f gives us first. And the G of n plus 1, we simply search for the smallest, we just define it to be f of m, where m is the smallest natural number such that f of m is greater than g of n. So we're defining by recursion, so we already know g of n, and because A is infinite, eventually we're bound to hit some element f of n which is greater than the number we're already at g of n. We simply return that one. So the first one we find. And of course, we don't get a whole array like this because in following this algorithm, we might later on find some smaller numbers that we omitted from our increasing sequence. And then it's too late to put them in because we're defining a total computable sequence. And we couldn't put them in because if we need to define an increasing function in order to get the set A is computing. So we have by construction that the image of G, range, let's keep the notation, range of G is infinite. Because for each n you get something strictly larger than for the previous n, and it's also a subset of n, obviously, because we're only taking values that are n of something. Okay. Right, so last week we had a very long Wednesday. So I think it's not unreasonable this week to have a shorter Wednesday, and that's the material that I wanted to present today. So if there are no objections, then I propose we end the lecture now. Are there any objections? No, jolly good. So are there any questions?
I mean, it's just a stupid quiz. Many of these like informal proofs look like if you can adjust somewhat more expensive programming language, you just write it in anyone way.
Like
one
yeah, so
is bounded execution, one is parallel execution.
Right, so indeed, if we had some more expressive programming language, then we could do all these informal, because they are informally computable, and you could have computational model that builds these things indirectly and make them formal. Whether somebody has done that in a study of computability theory, I don't know. You also want to keep your model of computation simple beginning, so you can, so you don't have
I mean,
too much.
I just really need to just add a function which is defined in this. And then
Yeah, but you'd be changing the model of computation if you add these things, like parallelism and stuff like that.
I
Well,
mean,
you don't need that.
I mean, if you could just program the infinite parallelism as a function, computable, then you can that way, not expanding. That's just
Well, you can kind of do.
I mean, yeah, why don't you?
Well, I mean, it's not that we only need to get it down to computable in the model we've got. So, so I'm informally describing how to compute it. You can go and dirty your hands with a Turing machine and implement that. Or we could have a lemma that tells us we can do parallel computations. But at this stage, we've got the Turing pieces, so we don't need to. But I'm not quite sure. Maybe I'm missing what you're.
No, it looks like lemmas are just to so that you don't need to program, so you make the lemmas. Why don't just program more primitives and then you them?
Oh, well, these which lemmas? So
I mean, whenever you build
I mean, all the characterizations today are very useful.
I mean,
Not just so you don't program, but in understanding.
I mean, you could, I mean, you could still prove them just by explanation, and it just nothing.
Okay. Yes. Okay, I'm not sure I completely understand the point, but yeah, we can talk about it offline. Any other questions? No. Right. So let's end the recording.